This common emitter amplifier is one which we're going to be solving in this video, and this video is made for TAFE New South Wales. I'm Greg Moore. I'll be using Camtasia, iCircuit and Notability software to do the recording. So I've got the simulator running at the moment. The simulator really does push the computer to the limit. What we've got here, we've got a common emitter amplifier, and we've got various switches in the circuit. I've got 1, 2, 3, 4 switches in the circuit. And let's examine what each switch does. The first switch, of course, is connected to the AC source, and that, when it's open, of course, isolates any AC from getting into our amplifier circuit. The amplifier is in common emitter. The transistor has a beta of 100. We have a voltage divider with 100k and 12k resistors. 470 ohm emitter resistor, and of course when the switch is closed I have that bypass to AC. When the transistor is properly biased, the collector is going to be sitting at the mid voltage VCE based on 12 volts and 0 volts. So we should have about 6 volts there, and in fact I've set up the bias on this particular amplifier so that it is what we call midpoint biased amplifier. This other switch up here short circuits a 3.3k resistor which is in the collector circuit. Here's my current from the rail to the collector. So at the moment I only have 4.7k of collector resistance going into the collector. This voltmeter here is measuring across these two resistances. At the moment one resistor is short circuited, so it's only measuring the voltage across 4.7k. The other voltmeter is measuring VC. It's not VCE. In fact, to get VCE, I'd have to get the voltage on the emitter and subtract it from that to have VCE. Let's have a look at the notes. Okay, here we go. Greg Moore, 2018. So, in the first slide, I've got no signal. I've got, so what voltage is here? Well, I've only got a DC voltage, and we'll go on and solve that in a moment. What does this switch do? This switch opens the capacitor from the circuit so that now we wouldn't have as much gain if we do apply the AC, because all of the AC, or a large percentage of the AC voltage would be developed across that 470 ohm resistor, and otherwise subtract from the gain which is possible in the amplifier. The other switch up here I've already spoken about. This switch here, I haven't spoken about this switch. This switch switches in the load resistance, which is 10k. It's coupled via a capacitor, so therefore capacitively coupled, 47 microfarad. At the moment, we do have that 10k load resistor in the circuit. So the circuit is drawn, as I said, in iCircuit on the Apple iMac. The simulator is slow to build the AC waveform sometimes, and that's probably an understatement, because with Camtasia running even with an i7 processor, we might run into a little bit of trouble. So let's examine the bass. I've used iCircuit simulator. In fact, look, what I might just do for a moment, while I'm not using that simulator, I might just pause that. That'll give me a little bit of headroom in the way of production. So with the simulator running, I touched on this wire and it told me that I had 12.12 microamps flowing into the base from my voltage divider, and the base voltage was at 1.16 volts. So finding V base, the two resistors form a voltage divider, the 100k and the 12k going to ground. So really 12k over 112k times the VBB should give me the voltage at that point. But we've got to be very careful. I've done that here and I get 1.29 volts, but I put it with an exclamation mark, no, because this forms a current divider. I have one current path going down here, I have another current path going in here. Therefore, that's not going to give me that voltage at that point. Simulator has a lower voltage. The simulator says that I have 1.16 volts. I calculated 1.29. Yeah, well, the simulator's probably got the right idea because it's taken into account that current. Now, how did the simulator achieve that? Well, when we look at this resistor and we see that we've got 12k, we have to multiply that by 10 to do some maths here. 10 times R2 is 120k, and we say to ourselves, is that less than beta times 470 ohms. Well, beta times 470 is 47k. 47k, that is not less than that. Therefore, we have to do a little bit more maths in the circuit to make things work out. So I've got the parallel combination of R in base, which is beta times the 470, to 47k. I've got 12k parallel 47, and that forms my new R2, or if you like REQ. So REQ over REQ plus the 100k times 12 volts, 1.05 volts. I was a little bit taken back when I did not get 1.16 volts. So I've got to ask myself here, I wonder what they've done in the simulator to get that 1.16 volts. If you have a look at the currents that we've got flowing here, there's 108, the simulator told me I've got 108 microamps flowing down through the 100k, 96 microamps flowing down through the 12k, and of course it was already given to us, IB was 12.12. I think what they must have, they've certainly got the 96.32 microamps, 12k, that's where we get the 1.156, 1.16 volts from. But I think the mathematical model that the simulator is probably using, they must be subtracting the 700 millivolts VBE from what you'd have with a barefoot voltage divider there, and then using this equation, VE on RE over beta. It's not exactly correct, but it's coming much closer to that 1.16 volts. And as I said here, I thought this was going to be easy. So, you know, we start looking at what's happening in a real circuit, and a lot of textbooks don't mention R in base and the loading effect that you've got and the different current and current divider here, and you're only told to work out R2 over R1 plus R2 times VBB, and that's 9 times out of 10 it's never going to be right. So you've got to think that out a little bit more carefully. Slide number 1, I've got an AC situation happening in our circuit. I've still got an unbypassed emitter resistor. I've got 4.7k RC, and I've got a load resistance of 10k. This was taken with the simulator running, and there was the AC waveforms coming in. I had 10 millivolts peak to peak coming into the base, and I got 64 millivolts peak to peak at the output. That's showing me that I've got 64 divided by 10 is a gain of 6.4 times. So why is that so? You can see here PP, peak to peak, 64.6 millivolts on the output, 10 millivolts on the base. And I've asked here, is this midpoint biased? It is in fact midpoint biased, and that's where we want a common emitter audio amplifier all the time to ensure that we get symmetry with the AC waveform at larger values. So if we take a bit of a look at this transistor, we've got to know about little RE, and we've covered that in the notes so far. It's always in the range of about 12 to 30 ohms, and in fact in here I've calculated it out to be 21 ohms. I've done the maths over here, 25 millivolts divided by the given current, 1.2 milliamps. There was the 1.205, stopping it at one instant in time with the simulator. That was where it's at, because with AC going in, you know, we might have some variations happening here in real time. Only small variations because we haven't got a very big signal going in. But you know, just the same, we're no longer, when we've got an AC signal coming in, sitting in our constant current region all the time, because the base current is changing with that incoming base voltage changing. So when I look at the gain in this, I have to know that RC is 4.7k, and in fact big R, big C is 4.7k. That's out of circuit. But what's happening with this 10k? 10k is connected to ground. Rail is a ground for AC, so in fact if you bring that ground down and put it next to this ground, you've got the 4.7k in parallel with the 10k. That gives me 3.2k. This is an AC situation, remember. So 3.2k, and then I have to divide that by, I've got to take into account little RE here. I've got to have big RE, it's unbypassed, plus little RE. I get a gain of 6.5 times. And that's pretty well exactly what I saw. I saw a gain of 6.4 times on the simulated oscilloscope, and the maths gives me 65 millivolts. So I've said that's not bad. That's exactly what we'd expect. And remember, VCE is dynamically changing. The CE junction is like a variable resistance across here. So how about VCE and VE? I mentioned before that VC was 6.275 volts. What about VE? Well, we have to work out the voltage across VE to be able to get VCE. So I've worked out VE was 0.566 of a volt, minus that from VC, and I got a VCE of 5.709. And that, when we're looking at midpoint bias, is probably more important to us because we have to think about that load line. The x-axis in the graph for the load line is in fact VCE, going from 0 to rail. 9 times out of 10, I mean, we've got a fairly small emitter resistor and we haven't got much voltage at the base, but if the voltage at the base came up, then that would be more important. This being only half a volt, we could have just looked at VC and gone, that's smack where we want it. Having looked at those mathematical points for the first circuit then, let's go and have a look at the simulator in real time. So let's hope that the simulator doesn't crash on us. Like I said, we are pushing things a little bit hard here. Just give it some time to settle down. Okay, that's settled down there. You can see I've got 64 millivolts occurring green to green, 64 millivolts peak to peak, and I've got 10 millivolts where the orange colour is here, peak to peak. So I've got a gain of about 6.4, almost 6.5 times. That's smack on what the math said. You can see these other values changing, because we do have an AC 10 millivolts peak-to-peak waveform coming in, and that of course is changing the base current, which is changing the parameters on the transistor to change the collector current, and therefore VCE and VC. You can see the values changing here. All right, we'll stop that and we'll go on to our next circuit. In the next circuit, I'm going to make RC bigger. So that's that switch at the top. By opening that switch, I'll now have 4.7K, 3.3K, that's 8K ohms of resistance. With 8K ohms of resistance there, I've still got my RL in circuit, so I need to have 8K in parallel with 10K to get small RC, which is our AC, like our dynamic collector resistance there. So, and then I've got to divide that by little RE and big RE. I'd already, when I captured this slide, 90 millivolts peak to peak, 10 millivolts peak to peak, so I've got a gain of nearly 9 times there. The mathematics says exactly the same. We should have a gain of 9 times because that 4.44K, that is in fact the 8K and the 8K in parallel with 10K, 4.44K. There's my equation, 4.44K divided by big RE plus little RE to get a gain of 9. So 90 millivolts, you can see I've got 90 millivolts in the original readings there on the oscilloscope, so that was perfect. Again, we'll go back, we'll look at that in real time. So I need to double click on that, that'll open that up, and run the simulator. I can stop that, and there's my 90 millivolts. You can see green again, 90 millivolts peak to peak on the collector, and 10 millivolts input, so a gain of 9 times, just what the math said. In scenario number 3, slide number 3 here, the previous one we had a moderately loaded amplifier, 10K, and we increased RC. Now in this third variation of the circuit, we open RL. So if we open RL, it'll be an unloaded amplifier on the output. Little RC, the AC collector resistance will increase. And because the collector resistance is on the top of the equation, therefore we're going to get a bigger gain. So that'll be straight 8K. I left the switch open, as you can see there. So I had 4.7 plus 3.3K. 8K, again, we haven't changed anything in the emitter circuit, so it's big RE plus little RE, 16.3 times. And the voltage gain seen in the amplifier was in fact 16.3 times. Here it is here. We've got peak to peak, 161 millivolts on the collector, 10 millivolts there. Divide that by that, we get a gain of 16 times. That's perfect. That's exactly what we wanted. So if we go back and we do that, open that up, run the waveform again. Sometimes it takes a little while to settle. There we are. Just so I'll pause that simulation. So no load. The switch is open, and the gain there is 161.5 millivolts that we have on the collector of the transistor. All right. In the next circuit, circuit 4, to again have little RC, 4.7K in parallel with 10K. So I've closed this switch again, putting RL back in the circuit, so that will be effectively in parallel with the collector resistance for AC purposes. The Q point is still centralized for DC at around about 6 volts, and RE in this case is bypassed by a 47 microfarad electrolytic capacitor. So any AC developed at the emitter junction is going to be bypassed straight down through that capacitor to ground. So all of the amplification takes place in the base circuit, and we're going to guarantee that we get the most amplification that we can out of this amplifier. So I measured that, and you can see here I've got 1,500 millivolts, 1.5 volts peak to peak in the collector circuit, and 10 millivolts here. So dividing those two out, I've got a gain of 150 times AV, A gain, V voltage, voltage gain 150. Note, no clipping or distortion. Midpoint biased, we've only got 1.5 volts, so that's 750 swing in each direction, millivolts. So it's not a really big excursion of voltage, and we'd have a beautiful linear output in a real amplifier based on that. And because we've got the two resistors that we have to put in parallel, the gain of course comes to 4700 in parallel with 10K. That we saw before, 3200 ohms divided by, look, now we get rid of big R, big E. We've only got 21 ohms on the bottom of the equation. That's why the maths tells me here that I've got 152 times gain. The AC gain will be quite large here, and it is. It's 150 times. It's really good. So what's going to happen if I make the collector resistor even bigger now? If I made the collector resistor bigger, I've got the numerator then being bigger, denominator still being tiny at 21 ohms. We'll see in the next slide. So, we're going to get bigger and bigger gain till somehow we might even crash. We'll have a look at that shortly. Before I go on to the next one though, let's have a look at that. That's, I've got to close that. And I think I had that closed, yes, and I had that closed, and yes, we've got 4.7K, everything's good. Okay, simulate it. Simulate it. There it is, and I'll just pause that. Again, look, why did it stop at 6.9 volts? It's because we've got the current changing, and that voltage is constantly swinging up and down at the rate of the frequency going into the input, which is 1,000 times a second change there. So we've got 1.5 volts peak to peak in the green occurring there, 10 millivolts there. So that's my 150 times gain occurring in that circuit in real time. All right, so on to the next one. Circuit number 5. On the next page, I disconnect RL. AV is now 4700 ohms divided by 21 ohms. And that gives me a gain of 224 times. The simulator gave me a gain of 221 times. You can see here I've taken RL out of the circuit, 4.7K big R, big C. I've got bypassed the emitter circuit. I've got no load on there. Let's go and have a look at that. So take that out and simulate it. And there it is. We can stop that. Pause that there. Stop that. And we've got 2.21 volts peak, so 2210 millivolts peak to peak here, 10 millivolts, gain of 221 times. And that's exactly what I had here on the recording before I captured that picture. Still no distortion, we're midpoint biased, and everything's still looking good at that point. Now, distortion. Eventually the gain may exceed the excursion limit set by the DC bias, and in figure 6 over the page, big R, big C is 8K, RL is going to be open, which is infinite resistance, so I've got 8K on the top of the equation. Bypassed amplifier, I've got simply little RE around about 21 ohms on the bottom. It's going to give me a gain of 381, but the simulator shows only 355. Why is that? Let's go and have a look at the simulator running to start with. So we open that, run the simulator. Okay, the simulator's settled down. I can pause that. I'll stop that, and I've got 3.55 volts, so 3,550 millivolts peak to peak here, 10 millivolts there. That's a pretty big gain of 355 times. But look at the bottom of the waveform. You can just see it's starting to get a little bit distorted. It's not round like the top. It's got sort of chunkiness. It's missing something there. It's in fact starting to clip. Let's look at the notes. Okay. Like I said, the simulator gave me 355. The maths give me 381. What's happened? We in fact have saturation clipping there. So, in this circuit, the amplifier is really working at its extremes. There's my large 3550 millivolts peak to peak on the collector, 10 millivolts peak to peak on the base, a huge gain, but look, I've drawn the rest of the waveform here, dot, 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 dot. There's what the waveform should have looked like. In fact, it's clipped off, and that's why the peak-to-peak value is at 3.55 volts and not a little bit more. And we have saturation distortion happening there, and we can see that because the load line, the Q point, has shifted. The Q point has traveled right up the load line, because I've now got too much collector resistance in the circuit, and the geometry of the circuit is pretty well modified without even the AC going in, and that's put it into almost into saturation. Remember saturation, if we get the collector voltage is lower than the base voltage, then we're actually into a saturated situation with the transistor. Here's our load line. There's where the Q point should have been, 12 volts VCC. And there's my VCC over RL, which is my saturation point up here. Well, the Q point has shifted from 6 volts down to around about 3 volts. That's actually gone up the load line. If we look at the current then, we're pushing in the signal. The signal is coming up here. It's hitting saturation when it peaks. And then it's coming back down. It's okay on this end, but it's only clipped on one side. And if we extrapolate that graph down to look at what's happening with VCE, saturation clipping happening on the low side of the waveform. If you turn your head to the right, that's what you're going to see on the oscilloscope. There's the positive peak is perfectly okay, but the negative peak is going to be clipped in that circumstance. So you could say we've hit the limit. In this picture on the right, we've got some pretty severe distortion. What I might do, I'll go back to the simulator in a second and I'll do this one. This one I've increased the V into 20 millivolts peak to peak, and you can see now I've got really severe saturation distortion happening in the circuit. So let's go and do that. I need to go to my input, and this is actually in this iCircuit. This is set up in peak. So if I go 10 millivolts peak, that's the same as 20 millivolts peak to peak. That's twice the input waveform that I had before. Everything else stays the same. Let's put it into motion. All right, it'll take a moment to settle down. There we are. I've stopped that, and you can see there that severe saturation distortion clipping on the bottom there, which is distortion. I'll just stop that simulator again. So we're really pushing this thing to the limit now. Look at the collector voltage at that snapshot point in time, 2.93 volts. You know, we've pushed the Q point right up to the far end of the graph there almost, and we are pushing that transistor into saturation. So that's a very undesirable thing to do when we have audio waveforms that we want to have nice fidelity and good linearity. We don't want to do that. In concluding this lecture, I'd emphasize the importance of digital test equipment, the oscilloscope especially, and the digital signal generator. You must be proficient with all of the test equipment. Labs have defined durations. You need to be competent. I still find people are just taking too long with the equipment, and we really do not have the time to spend with the equipment. You know, if we've covered the equipment once, you're expected to be able to keep competent with that for future lessons, and not have to work out what control settings have to be and how to read things on the screen. And don't forget, repeating units costs real money. And in Chinese, I'd be saying Ting Wo Shuo, which means listen to what I say. Make sure that you know this stuff, because it comes very fast in amplifier fundamentals. All right, this has been Greg Moore for TAFE New South Wales. That concludes this lecture on common emitter amplifiers. Thank you.